All right, guys, so we are at this particular point where we learn now that Howard actually simulated this SIR system. We think that it was a highly virulent flu epidemic, all right? Because if you look at the RE there, it's 3.5. It means that one person was getting like three people that he was going to, like four people, 3.5, so like four people that one person was going to infect. So that was a high transmission of the disease, and we expect that it must not take long. That's what we expect. So you look from this graph that we are given, this plot that we have got quite some things that are interesting there. We have if you look at the red line is for the recovered. So you see that as time moves, people recover from the flu. And I don't know what this time is in. So it is very important whenever you create your own plot, you must make sure you tell us that the time here, what is on the x-axis, what is on the y-axis. So you must label your plot, but so this is the population for the number of people, and this is the time. I think in days, it's a flu, so it can take up to 100 days, right? Or yeah, days is better. So we are having people that are having a flu here, and that flu died out after some time because 50,000 people were susceptible, and the number of susceptibles was going down. As you can see, it's going down, but as it is going down, something is going up as well. The number of infected is going up. Up to this point, this is the maximum number. Remember what we were saying, that can increase. So it increases, gets to a maximum, starts decreasing, and that is the characteristic of an epidemic. So we want to try and reproduce this graph and see if we can come up with such a graph in Python. That's what we want to do. So to work in Python, what you need to do, I use Collaboratory. So in Collaboratory, you just go collab research google.com, and then you just give a title, and we are going to say the title of our work is Howard, because we are following the work, or let's just say flu. All right, that's the title of our work. It's called flu. And after doing that, what we need now is to import some packages. We need the numpy package, which is so import numpy. We import it as what? As np. All right. So this is important because the numpy package, which we call np, is an important package because it contains the libraries, numerical computing libraries for Python. It provides support for large multidimensional arrays and matrices, collection of mathematical functions to operate on these arrays. So that's what it does, all right? And then the other thing that you need at the same time after importing, our system is very simple, so we don't need something complicated. We need also some integrate, because solving the system includes integration. So we need to have SciPy integrate, which is going to help us as well for solving ordinary differential equations. That's what it does. Then, because we are going to have a plot, we also need to have the matplotlib library. So we are going to have that as well, and say so. The beautiful part in Python, when you are working in Collaboratory, you can always run from here or use Control Enter. So you can just run from there, and you can see that you have imported. So it will give a green tick there if you have done things correctly. Let's wait and see. It's importing those libraries that we were talking about. Then from there, we now need to see, so it gave us a green tick, so it means everything is all right, because if everything was not all right, then we're going to have problems. Then I prefer to create a new cell. So this is done. Then we've got a new cell where we now declare our parameters. If you look carefully, we were given that beta is 0.7 over 5, 50,000, V is equals to 1 over 5, S naught is equals to 49955, I 0 is 5, R 0 is equals to 0. So we need to declare these first in Python, and then only after declaring these, then we can move on to something else. So we declare it over here. Let me see if I can quickly, because I've done this work some time back, so I'm just moving on quickly. So this is everything that we've got, and you run again, and then we get the green tick, which means that everything is all right. You come just down here, it will give you an option to create a code. If you come up here, it will give you also an option to create another cell in between these two cells, but we want a cell below this cell, so we just click there. Then the next thing that we need to do is to give our initial conditions. We declare them. So we know that we've got R naught is 5, I naught is 5, and S naught is that. But now we want to have the symbolic declaration. So it's a list that represents the initial conditions for the SIR model. And you see now, that's why we need that NP module, because it is there for matrices like this. So I've now declared the symbolic, not the symbolic rather, but the initial conditions. I've got the values here already, and now I'm saying these are my initial conditions, and we get a green tick to say that everything is all right. You create another section, another cell there, and in that cell now, we are now going to talk about your time points. So these are the time points at which the solution will be computed. All right. So what do we use to do that? We use the linspace. So the linspace np.linspace. We use that to check the time points at which the solutions will be computed, and we can like so we are simply saying that, look, between 0 and 200, then from 200 to 1000. These are the time points, and this is the time span as we need it. But we saw in the model by Howard that he was going all the way to 100. So maybe we go from 0 to 50, then all the way to 100. So this is what is happening. So because we are trying to simulate, to replicate his work. So we tick that, and then we win there. So this is our time grid. And then from there, now we bring in our function that is going to do the work. And our function is a function that is going to define the system of differential equations for the SIR model that we have got. And remember, we declared y0 here. We have got y0 as our initial condition. So it means that y is equals to SIR. So these are the initial conditions for our y. So y0 is the initial condition for y. So we are also going to talk about that. So what then do we do? So this is our function. I will talk a bit about the function, but I need to create a cell for the function, and I put it there. All right, so SIR model differential equations. So my function name is deriv. That's the name of the function. And y is made up of these three variables, S, I, and R. But also y stands on its own now as a parameter. All right. And we've got parameter t, we've got parameter beta, we've got parameter nu, we've got these. And as you can see, if you highlight there, it will give you the value that we declared up there. All right. Then we can see that now we've got the differential equations. These are the differential equations that we have got. You can choose to put a line there if you want, but then you must remember that you need a line there as well. But we don't want to put lines there, so we are just going to leave it as it is. So this is the differential, the system of differential equation that we started with, and we've declared it here. So what are we asking our function to do? We are simply saying that for these values that we have given you above here, please can you solve this and return to us the SDT, the IDT, and the RDT. That's what we're asking this Python to do using this function. It is going to collect S and I and R, the time, the beta, the new, and then for this particular system, this is what we are going to get. So we run this and it is successful. Our function is okay. Sometimes you find problems like, let me just move this and you will see that I've got a problem. And the problem is indentation. All right, because this is supposed to be a little bit inside there like that, and still I've got the problem of indentation until everything is in a straight line like that. Now you can see that there is no problem and we are good to go. Then the next thing now is I want my solution. So I have asked it for it. I've told Python what to do and to return this, and then now give me the solution. Give me the optimal values, or rather the values of given everything that I have given to you. You must solve the system of the ordinary differential equations using that function derive and using my initial conditions y0 and at the time points t. And then you must keep those as my solution. So we are going to ask it to do that. So it's going to integrate the SIR equations over the time grid, and then we get the solution. So it means that we are going to look at time 1, time 2, time 3, time 4, getting solutions at every point. So there we go. And then we are going to have what we call a solution. All right. And I wonder what happens if I write there and say solution, just to see if I get some values, because I must get something out of there. Yes, so these are the various solutions that we are getting at every time point over 100 time points. That's what we are getting there, to say at time point so and so this is the value, at some time point so and so this is the value. But this is not what I want to do. I'm good or better if I plot the solution. All right, so the plot of the solution is going to look like this. All right, let's talk about this. So we are going to plot the solution for the susceptibles, the solution for the infected, then the solution for R. All right, and we are going to label the graph the plot that we get as susceptible, the graph that we get as infectious or infected, then we have got recovered. Then what we are also going to do is our x-axis, plot x label. This is our x-axis. It's going to be called time. Like I told you that you must have labels for your graph. Then the y-axis is going to be called population, and the title of my graph is SIR model. I can change this to anything I want. Then I also need to have a legend. So I'm telling Python to say, please show me the legend. And then finally I'm saying, give me my plot. And if we run this guy, I just have to remind you that we are trying to duplicate this graph that we have got there, and we are trying to do that in Python. So if we run this guy, it must be that there is a good green tick, so our graph must look more or less like what we have got, which is what we have got here. So obviously we can see that our graph is going from time 0 to 50. All right, and what could be causing that is the fact that we cut something along the way. Let me just put this back to 100 and then push this to 1,000 and see what I get after that. So you have to run every cell now, because so now I've got 100. All right, fair enough. So now I have got 100 up to this point, and if you look at this particular graph that I've got, and the particular graph that we have got here, they are the same. We have managed to reproduce the work by Howard in Python. And as I told you earlier on, once your work can be reproduced, then you have managed to actually come up with a good article. But then what needs to be done at this particular point is looking at the graph itself and say, does it make sense? Yes, the number of recovered is increasing to 50,000, while the susceptible is becoming 0, and the infected are also becoming 0. And in that regard, well, they are not, the susceptible are not really 0, and also, as you can see, the recovered are not really 50,000, and you can see that the disease is gone. You can see that the disease is gone. It's now at 0 there. We don't have negative values. So like we said, that we were expecting our solutions to be positive at all the time. This is interesting. We need to do some work on simulations a lot, because especially with regards to bigger models.